So hello, everyone. Can you hear me all right? All right. My name is Ryan Johnson, and today I'm going to be talking about a vulnerability that was present in Samsung Android devices. So today we're going to talk a little bit about Android. Then we're going to talk about intent messages. Next, we'll talk about intent injection. Then we'll get to the actual vulnerability. Next, we'll talk about impacted versions. And then we'll talk about use cases that we dynamically confirmed. Next, we'll talk about disclosure timeline, and then wrap it up with some conclusions. So for this research, I collaborated with Angelo Stavro and Mohammed El-Sabag. So we all work for CryptoWire, which was jump-started by a DARPA project back in 2011. We've also worked with DHS, S&T, as well as NIST, which are government organizations. So at CryptoWire, we do software assurance, developer integration, mobile device management, threat feed, and security analytics. So over on the right, you can see the Android software stack. And where we're going to focus today is up at the top on the system applications. And Android makes, or Google makes Android open source via the Android open source project. So Android's an open ecosystem with many vendors creating Android devices. So they will fork a version of Android and then make their own modifications to it to somewhat differentiate themselves in the marketplace. So these customizations are great in that they add extra functionality that was not there, but they can also introduce vulnerabilities because it may not have, the code changes may not have the same visibility that is present in AOSP. And some of the Android vendors have their own security bulletin, such as Huawei, Motorola, Nokia, OnePlus, Oppo, and Samsung for when they do introduce a vulnerability based on the modifications that they do make to AOSP. So the system apps, that software layer we're going to focus on here, calling it pre-installed apps. And these are just any applications when you get an Android device, power it on for the first time. These are the applications that are present that you did not install yourself. So some of these applications cannot be uninstalled. They're just present on your device. Some of these applications cannot even be disabled. So if there's a vulnerability in one of these applications, then you essentially just have to wait until there's a software update that patches it. So some of these pre-installed apps run with special UIDs, which kind of what we're going to focus on today is a system user, which uses UID 1000, but there's also radio, which is for phone, Bluetooth, key store, NFC, and secure element. So these pre-installed applications, by their nature of being pre-installed, have access to permissions that are not available to third-party applications. And a third-party application is an application that you install from an application marketplace. And an example of a permission that a third-party application cannot obtain is the master clear permission. It has a protection level of privileged and signature. So privileged, that's just a pre-installed application. And signature requires that for an application to get this permission, it has to be signed with the same cryptographic key as the application that declares it. And this is declared in the Android framework, which runs as a system user. So speaking of Android applications, they are composed of app components. Android apps are not monolithic. They do not have a single application entry point. So these application components, Android provides in the framework activity service, broadcast receiver, and content provider. So an application developer will extend these framework classes and provide their own application logic in the callbacks. So for the Android system to be aware of what application components are within an app, each valid Android app must have an Android manifest.xml file. So the system parses this and it tells the system what application components are contained within the app. Also, there's a declaration there for an activity. So that just contains the name, any access requirements with regards to permissions, and intent filters. So an intent to communicate with application components, this is done through intents. And an intent is essentially an abstraction for a message. So if you want to, this can be sent within apps or between apps. So in the example here, application A is going to send an intent message to application C using binder as the transport. So in the code example, application A creates an intent, uses an action or an action string denoting an abstract action. It happens to be call privileged and then provides a URI, which is a phone number. And it sends this intent, which to the system, and application C registers for the same action. So the system resolves the intent and routes it to application C, and application C receives it, and then it can get whatever embedded data is contained within the intent and process it. So intent, the intent message internally has a field which is a bundle data type, and a bundle data type essentially stores values as key value pairs. So a bundle can contain primitive data types as well as arrays and any objects that implement the serializable or parcelable interface. And the parcelable interface allows for quick serialization where you explicitly create routines for converting the object to or from the byte stream. And the intent object itself, it implements the parcelable interface. So this allows an intent object to be embedded within an intent object, and it can be nested arbitrarily within an intent object given the constraints on memory and all that. So here is, we're going to talk about intent injection. And here, application A is going to create an intent in yellow, which is to essentially call 911, which is an emergency number. It creates a second intent in blue. And then it's going to embed the first intent into the second intent using a key name, which is extra call intent. It sends the intent using an action string of user select Wi-Fi call to application B, which registers for it. It's going to receive that intent, get the embedded intent using the same key name, and then send the intent, which then will reach application X. So application A has created an intent and sent it indirectly to application X through application B. And when application X receives the intent, it's going to see that it comes from application B. And since it's sent from application B, it's going to be sent within its context. So if it's a privileged app, it's going to be sent with all its permissions and capabilities. So there's the Telecom app, which in Android devices, according to its documentation, it implements the Telecom framework service, which manages audio and video calls on an Android device. So the Telecom app is open source. You can see it, browse the code, or you can fork it. This application is generally modified by Android vendors, and it executes with the system user ID, which to do this, an application will need to use a shared user ID of Android UID system and be signed with the same key that signs the Android framework. So we looked at, for a concrete example, on the Samsung S21 Ultra 5G, which is running Android 12. The build fingerprint is provided there. This application itself, in its manifest file, requests 47 different permissions. But at runtime, it has 420 permissions granted to it. And this is because when an application uses a shared user ID, any other applications that use the shared user ID, they pool permissions together. So any permission which is requested by any app that runs as the system shared user ID is available to any app that runs as the system shared user ID. And if you use ADB, Android Debug Bridge, you can just execute that command, shell, ADB shell dumps this package, and the package name. This will show you the permissions that the application requests itself, and then also the permissions that the application is granted at runtime. So Samsung has modified the Telecom app to add in additional application components statically that are present in the manifest, as well as dynamically, which are broadcast receivers which can be registered at runtime for specific actions. So coming to the vulnerability, in Samsung Android devices, local apps can use the Telecom app to start arbitrary activity application components on its behalf, as running as the system user and all the privileges that are granted to it due to a broadcast receiver application component which lacks access control. The CVE is provided there. It has a CVSS 3 base score of 7.8. And the goal would be privilege escalation by a local application using an insecure application that's privileged, having it perform actions on its behalf, which it does not have the permissions or capabilities to do so. And using this, since the Telecom app is running a system, it can start activity application components which are not exported. And when an application component is not exported, it cannot, in the general case, be started by other applications, although it's running as a system user, so it's considered part of the system. And the Telecom app has a large amount of permissions that are granted to it, so it's quite privileged. So here, kind of somewhat of an abstract workflow for the vulnerability. There's the Telecom app. It registers for the user select Wi-Fi service call action. Then a malicious app that's co-located on the device creates an intent that it wants to send, embeds it into a second intent, and then sends it to the Telecom app using the user select Wi-Fi service call action string. By broadcasting it, the Telecom app will then receive this intent and then extract the embedded intent and then start it as an activity, which will then be sent to the ultimate target application, which will then essentially receive the intent and perform whatever action according to its application logic acting on the embedded data. So here's a more concrete workflow example. We have the malicious app. On the Samsung devices, there's a com.sec.factory application. There's within that a activity called factory reset. It creates an intent for this activity, puts it into a second intent, with the second intent having an action string of user select Wi-Fi service call, sends it to the Telecom app. The Telecom app extracts the activity application component and then sends it on to its destination, which was controlled by the malicious application. So it gets sent to the factory reset app, or factory reset activity within the device test app. The device test app, here the factory reset activity is not exported and it's protected with a permission, although both the Telecom app and the device test app are running as a system user. So the Telecom app can start it. And the application logic for the device test app is to, upon starting this activity, send a broadcast intent with the master clear action string, which this in Android is going to be received by the master clear receiver in the Android system, which will then programmatically initiate a factory reset. This is done with the recovery system API or reboot wipe user data method, which then boots into recovery mode and wipes the data partition, which contains the user's applications and data. So the root cause of the vulnerability is the telecom service application component, which will run at startup, and it sets up various managers, including one that handles Wi-Fi calling. And for the Wi-Fi calling, there's a class called Samsung USA WPS broadcast receiver. This registers for the user select Wi-Fi service call action, and it doesn't require any permission. So this allows local applications to send it broadcast intents, which it will then extract an intent from and then start it as the activity. So the threat model is a local app on the device that doesn't require any permission, so it may appear harmless. Although if you were actually doing this, you'd likely want the foreground service permission just so you can run as a service in the background, although the foreground service does have a notification in the notification drawer. We don't assume any user interaction, and the goal is to indirectly obtain privileges via privilege escalation by sending broadcast intents to the Telecom app for it to extract the intent and then start it as an activity. And since it is an activity, there is likely going to be a GUI component to it, which using the same vulnerability, you can start an activity to request the home screen or the launcher to remove whatever lingering activity was present. So this vulnerability has, at the time of disclosure, which was November 25th, 2021 to Samsung, was present in Android 12, Android 11, Android 10, and also Android 9, which Android 9, the vulnerability is slightly different. It still uses the same insecure broadcast receiver with the same action string, although in Android 9, instead of starting arbitrary application components, it will send broadcast intent. So the attack surface is different. So on 10 to 12, the attack surface is activity application components, and on 9, it's broadcast receiver components. So using, it's essentially done in the same way where it extracts the intent and then it will broadcast it. So using this, you can use the extensive permissions of the Telecom app. You can also send broadcast intents, which are protected broadcasts. And broadcast receivers don't have a GUI component, so this is going to be done in the background. And at the bottom is a POC code example to programmatically wipe the device. So here on Android 10 to 12, we provide some concrete use cases, which on the left shows the capability, what we were able to do. And since this is being done through the Telecom app, which has the requisite permissions to perform these behaviors, our local application that's malicious does not. So for each of those capabilities, we also show the permission that was bypassed. So all of the permissions except for call phone are only available to pre-installed applications, which call phone, that's a dangerous level permission, which will have to rely on the user to grant to an application. There's also additional unexplored capabilities. We provided some, but the attack surface is pretty great, just all the different activity components which are accessible to the Telecom app. So one of the capabilities is installing and uninstalling apps. So there's a few things that you may want to do. So installing an app, you can start with an app that has no permissions and then install an app which requests that you have embedded within the malicious app, which requests all permissions that are normal level, which are granted to an application at install time. On certain Android devices, we've seen some capabilities be pre-granted to package names which are not present, where it will only consider the package name and not actually look at the signature, which obviously is insecure and doesn't really provide any authentication at all. So that can be taken advantage of just by installing an application with a given package name. And you can also install applications with a lower target SDK level, which may have greater ability to perform certain actions based on backwards compatibility. So for uninstalling apps, you could do this to weaken system security by any AV application or any applications that are performing health checks. You could remove those, assuming they're a third-party application. If there has been an update to a pre-installed system app, you could uninstall the update, which may regress it and cause a vulnerability that was patched to be unpatched. And if there is a third-party screen lock application, you could remove that to get access to the device. And then using both uninstall and install capabilities, you could uninstall an application that the user has, say WhatsApp, and then install a version which is repackaged, which is malicious and leaks or obtains the user's credentials and also steals data. So here is the code to uninstall arbitrary applications. The target application or activity component is not exported. It's in the standard package installer. And the activity name is called uninstalling. So here it's going to uninstall a screen or a third-party screen lock application, which is in blue. So just uninstall. When you provide the data that uninstalling activity is expecting, the behavior of it is to essentially just programmatically uninstall an application. You can also call arbitrary phone numbers. So here you provide a URI, and some of the action strings are call, which is for placing normal phone calls, as well as call privileged, which is for emergency numbers. And the code example there is to call 999, which is the emergency police number in Singapore. And the screenshot on the right is for calling 911. So here we have a video where there's an application that's co-located on the device, and It's going to programmatically initiate a phone call. And they're going to pick up, and I'm going to exit the call. Next is calling emergency phone numbers. So the co-located application is going to call 911, which you need to hang up pretty quickly on that one. And for installing arbitrary applications, this co-located app, the POC app there, is going to install a terminal emulator application and then dismiss the activity that was left. There's the lock screen application. It can just uninstall the application, any third-party application that is present there. It also has the capability to spoof arbitrary apps. So here is the legit Facebook application. So just showing the GUI, it's going to uninstall it and then install a fake version with the same package name and icon and application name. And here just showing that we can control that application. And then also you can programmatically install a certificate authority. So here's just a screen showing we installed the man-in-the-middle proxy root certificate authority, which undermines TLS and SSL, which is used extensively in HTTPS. Here is performing a programmatic factory reset, so just running the application. It sends this is on Android 9, the factory reset action string, which is then received by the Android system. And it's going to boot into recovery mode, and then it's going to erase the data partition, which contains the user's installed applications, as well as all application data. So we've talked about intent injection. So some of the defenses where there are these activities which, when started, are going to perform a privileged action. And for some of these, say, like wiping the device or installing a certificate authority, you could put the user in the loop where it provides a dialog where the user can either reject or accept this action instead of being performed programmatically. There's a class in Android called pending intent, which once you create a pending intent, the application that creates it can create an intent, pass it to another application, and then once that pending intent is sent, it's going to be sent within the context of the application that created it and not the application that sent it. So you can maintain the context of the application that created it instead of just the last application in a chain that happens to send an intent. And if pending intent objects can't be used, you can at least perform some filtering. Maybe you can put in a explicit application component destination, or at least filter based on action strings and not have it be completely open to performing any, sending any intent. So here is the timeline. It was reported on November 25th to Samsung. 2 days later, they acknowledged the submission. And about 2 weeks later, they confirmed the vulnerability and then rated it as high severity. Then on December 30th, they reserved a CVE. And on February 7th, they initiated a bug bounty, $4,300 through BugCrowd. And February 11th, the CVE on the National Vulnerability Database became public. And Samsung wrote about this vulnerability in their February 2022 security bulletin. And to conclude, so you would want to use some defense in depth principle and kind of assume that even if you do have this activity which is not exported and is protected by a permission, that maybe there is some vulnerability which a local or remote actor could exploit to actually start this activity, which, like in this case, we see it can be exploited locally. So one way to at least put the user in the loop is to, for some of these privileged actions, rely on the user to either confirm or deny this action from proceeding. And in general, in Android, any application component interfaces, you want to exercise proper access control, whether they're exported or not. And where possible, you should prefer pending intent objects over intent objects, just because that diminishes the effectiveness of intent injection. And privileged pre-installed software requires security vetting, just because it runs at such a high privilege level, it can have an adverse effect on the end user if the vulnerability is discovered. And that concludes the talk. I'd like to thank you for attending, and if anybody has any questions, thank you, everyone.